Hello, in this video, I'm going to walk you through another example called remove first. Again, this is from chapter 1 of EOPL version 3. I have this repository that has all the source code. We can copy and paste. So remove first is a procedure given a symbol and a list of symbols, or doesn't have this symbol, it can be numbers or any atomic values. And then it's going to remove the first occurrence of this element in the list. So we're applying recursive thinking, and our solution is recursive based on the definition of the list, right? So a list can be an empty list or a element and the rest of another list in a cons pair, right? So recall that this is how we construct lists, how the internal structure look like. So a list has a backbone, and then we start with the cons pair. The car is the first element. The curter of the pair is the remainder of the list, which is a list, right? A shorter list with a backbone. If you trace the curter, it takes you to an empty list. So based on this observation, we can write our program accordingly. So I'm going to go back to my previous version. So I'm going to copy this code, and then I'll put it in my editor. So okay, let's look at it. So this follows the definition of a list of symbols, right? So the list of symbol can be empty, right? That's according to the grammar, the first possibility. So if it's empty, then we're going to return the empty list, right? There's nothing to remove, and we get the same thing back. Okay, I'm going to run this to show you this as the correct behavior. Empty list. Oh yeah, actually remove something from empty list. So you got to give it a symbol, and it's empty list. Okay, so otherwise we are going to look at the second case, right? It could be a cons pair with a symbol, and then the curter is another list. So how do we implement this task? Well, we take it apart, right? We look at the car. If the car of the list matches what we're looking for, we're going to remove it, right? What is the result of removing this element from the list? It's just the remainder of the list, right? It's the curter of the list, which is which is the remainder of the list, right? The curter of the first pair. And then otherwise, we're going to skip the first element, right? We're going to remove the first occurrence of the target from the remainder of the list. But on our way back, after this recursive call returns, we need to we put cars of the list back. So this is called the curter down, cons up pattern. So let's try it. So if we do this, it's going to remove the first one. If the target is not the first one, it's going to remove it just fine. And it can be the last one. Okay, so we can trace this by commenting out this line of code. Okay, we're going to trace remove first. Okay, I'm going to run my definitions and then try it. Okay, so let's look at the tracing. Okay, we're going to call remove first the first time with the whole list, right? And then according to the algorithm, if it's not empty and the first element in the list is not the target, so what we're going to do, we're going to call remove first recursively with the same symbol, same target, but the remainder of the list. But it's indented because there's a pending operation there, right? On our way back, we're gonna add another const pair with the curter, okay, of the original list, which is C1, and the and then the result of this remove call, right? So this remove call gonna return C1 A4 because its car is equal to A4. Now we have the remainder of the work. So the car of so C1 is there. Okay, on our way back, we're gonna finish the appending, the pending job, which is to prepend C1 to the result of this remove call. Right? So we have C1, and then A4, right? Which is the result of this the first call, right? So the end result. So we have the list with A4, the first instance A4 removed, right? So that's that. And then okay, let me show you one more thing. So the list doesn't have to be nothing. If we do, okay, let's do this. If we want to remove a list with just A4, so I think we could do that. Okay, so this, it's gonna allow us to remove the okay, so I think so this is okay. This is because of the equivalent, so they're not equivalent, so it's not removed. So before, like, if I change it to equal, I'll talk about this in another video. So depends on how we check equality. Things may come. Okay, so now we get the second removed because this is indeed structurally equal to that. It's not equivalent, so the equivalent procedure predicate didn't work, but equals does work. So that's again another example of a list processing procedure that is defined based on the grammar of the list, right? So I think I pointed back to this. So this is a good mental model, right? When you think about list, think about a sequence of const pairs linked together as a backbone, and with a empty list if you trace the curter, right? And then each element can be anything, can be a primitive, can be another list, can be a list of lists, so on and so forth. So this is a very flexible, very useful structure. So we're going to use it to define all kinds of structures from now on. Okay, I hope this is helpful to you.